All right, well, good afternoon. It's Monday, 25th, so 24th. And today, as has been my want or habit for the last couple months, is every few days reading some books and just and making a running commentary, a rambling, that I ramble, soliloquize, extemporize to relay in a usual stream of consciousness assortment with an incremental and linear of sorts development of terms. I started just kind of warming up with reading this book on home, or some pieces from it really. There's not much time to actually read an entire book, like a book on tape or something like that. Although I suppose these days I could figure out how to get a computer to synthesize most of my voice and diction and indicate to it various ways that things should and would be read. I've gotten recently a good book on grammar, and it's called Calm, and it's a grammar textbook from about 1920 or 1930, and it's from England, say, but it encompasses American and English usage and tradition. And what it is a book on grammar, and that our grammar, I've been reading about the appositive and how the adjective and adjectival force is used in so many different things, and about the reference. And one of the things I've been studying and trying to, for example, write a program to do things in such simple terms as English language, or to write mathematical proofs in English language that happen to be demonstrably provable in a formal logic and as a symbol logic, and have normal forms as symbolic logic. That as I've been reading these books, I started in that manner, and in about 10 or 15 minutes I was able to pretty well exhaust myself. And then every few days, just been reading a bit more and more, so it stretches out to about an hour and what. It's not really any particular subject, except it's the subject of thinking writ large: philosophy, mathematics, and logic, and thus natural physics. And the key part is that it's thusly the natural sciences, physics, arises naturally from this thing. Now, if you kind of follow the field or read the science section of the news, sometimes you might have heard of mathematical hypothesis, mathematical universe hypothesis, that really the universe is kind of all these things together, and anything that's in terms of the numbers and geometry really is in a sense real and embodied. This is kind of a strong mathematical Platonism. The idea that a hologram forms from a continuum, which looks like a circle, and that is a line, and given we only have a spot on it that looks straight off forever on either side, and then that to the left and right somehow fit naturally these other spaces for 3 dimensions is why 3 space dimensions stand up, that and the ray of time reaches that, time goes back forever, and then space goes on forever, and it goes forward in time in space. That this kind of notion of the space-time, with the 4th dimension basically being our abstractly objective perspective on this as thinking beings, that it arrives at thusly a continuum makes for that there's a way to approach why there is basically a natural reality. And that then what's so great about that is that it's possible to arrive at things like that from the fundamental principles of that there is a continuum, and that it's this line, or it's this spiral space filling curve, our measure of it, or an analytical unit, an analytical unity, that following these kinds of terms of a dualistic monism, this dually self infraconsistency, as I put it, what's called the dualistic monism to be very inclusive of all cultures of the world, their usual dualistic monism and their dialectic, that it so arises then geometry, which is all matters of shape and proportion, which for many people is mathematics, is what can have shape or proportion and form. And then that these higher level mathematics and their symbolic and abstract forms so often become divorced from what people think is attached, that the connections become tenuous, whereas really they're as strong as anything else, or as loose as anything else. They're loose approximations or strong approximations. That these are the kinds of things that become very satisfying in terms of the compelling, what is beautiful in a sense, and thus for its own sake is efficient in terms, or that from the outside all this potential adds up to the classical in the middle, that it's the absolute that makes our classical view, is again this sort of paucity, an efficiency, a miserliness, if you will, but really just the fact that there's the principle of least action, the principle of not necessarily least surprise, but the principle of constancy and variety in diversity, and that it arrives at quite a manner of thinking that is by no means new. This is, in a sense, incredibly old-fashioned. And at the same time, it reflects what's new, because since the 20th century in quantum mechanics, in the fourth dimension, time is as an abstraction and the very nature of abstract thinking about space and time and the objects within it, as we are, in a sense, that the abstraction makes for a course forward. And so that's something that is by no means new. It's very old-fashioned, but it's new again in a sense that what now has arrived at our science, and in the middle is all the classical, that's rebuilt with his super-classical notions, like you've been thinking about infinity and a circle of the continuum and this kind of thing, that where those are as well ancient traditional classical notions, as we've been reading about the symbology of things and the phenomenology of things, that it becomes very new again, because now it's built atop the modern edifice of foundations in the logic of the philosophy of reason and philosophy of logical objects, philosophy of mathematics. Why then it's arrived at then these fundamental underpinnings that provide an intuition for constructivism in the space and range of the, how you might say, fundamental space, of the geometry that arises, that then the physical objects are so emergent that it makes it very possible to then approach this super wave, the superclassical, supersymmetry, supergravity, and these sorts of things, which make for then what was the classical mechanics of motion and the classical mechanics of electricity and magnetism, that then for our field theory, which is today's version of what theory is, a space-time with field occupation numbers of all sorts of various fields that combine, that the various forces in these fields, which are the propensities or tendencies of things to oscillate and they're stative, and to dissipate in the attenuative, that again, as was mentioned before, there's a strong nuclear force which holds atoms together. It's a sort of a fall gravity, that then the weak forces as above that, and they're unified with the charge carrier being the atom, and then bosons, or as it were. And then for the electrical charge, the force of electricity, and charge is the force carrier, that then that's two forces yet. And then there's the electroweak, that these are the four fundamental forces that are so far involved in unified field theory, the grand unified theory of a theory of everything, and the gauge theory. What is a gauge theory in terms of any torsions? Is that being the only things different than a Euclidean space, a de Sitter space, making any de Sitter space or non-conformal geometry. So, and that's for singularity theory and this kind of thing in terms of singularities as exist in the universe. So anyways, in these field theories, then it's possible to unite the force of kinetics as for massy bodies, that mass is the quantity, and the force of electricity and electromagnetism, that charge is the quantity, and that then this lives in this virtual Dirac positronic sea of space-time, which are virtual, constantly annihilating positrons and antipositrons everywhere, of that are the background of this flow of the continuum mechanics of matter and massy bodies, and electricity, and or motion in the electrical field, and charge. It's a unified field theory. And that it just kind of arises from this idea of the fall gravity, that instead of that gravity is two objects always pull together, they attract each other and come together. Instead, it's that the bodies fall together because there's only an infinitesimal gradient as from the outside. So it works out that this way, it again becomes a unified field theory. So as I've been recording these podcasts or talks and these readings of these books over the past couple months, every few days, that has been the background that I'd already developed. And so then looking into the pages of these books, what I'm looking for is that these, what then I can tell from the course that they have, the linear curriculum, if in the nonlinear spaces and these fields of potential, what it really means from this intuition that's developed first, that from having, for mathematics' sake, the line continuity, the field continuity, and the signal continuity, then it arrives at ways to deal with the Jordan measure and the Dirichlet problem, either side of what's otherwise these continuum mechanics, where the particle mechanics is just a grainy measure of sorts. It's the tweezers we have that are microscopic that can deal with something when we try to measure and observe things with the sampling, observer, and measurement effects of quantum mechanics, that it's really a continuum mechanics. And so that having the mathematics of the continuum this way, and the mathematics of infinity this way, and the infinitesimals, and the analytical nature of the numbers, for example, between 0 and 1, or between negative infinity and infinity, that they're real, albeit non-standard, applications of these, that once those equip the intuition with the ability to then make a place for what is the supermodels, the superclassical, that light is pretty much as of breaking radiation, and it comes in from all sides, that this fall gravity or is the shadow gravity, it's not a push gravity as Newton's is a pull gravity, but that is the full outer complement of this, that in these inner and outer products of these, as we've discussed, for all these structures that become discrete and rigid and lattice-like in the middle, still yet all is emergent from the continuum in this. So then, for example, I picked up this book the other day, and it's from a symposium, and it's about Markov processes and potential theory. So what is a Markov process? Well, you think of a process as the behavior of a number over time. And so a Markov process is the application of a formula or of a function that at any given time arrives at what is the development of the value of a given real number. So let's see that this would not be an introductory book. But what it has particularly is it's about Markov processes and potential theory. That the potential theory is more as relevant in these developments than the classical theory. And so from reading this, it wouldn't necessarily have introductions that you can find on Wikipedia. And Wikipedia is to be well regarded as a very comprehensive and much improved development over time for many more particular and detailed subfields of mathematics and physics than it once was, or 10 years ago, or 20 years ago, where such materials as this would only be available in a well-stocked university library and sometimes under lock and key. That these sorts of things about Markov processes and information theory and signal theory and that come along with it, and Monte Carlo and such notions of the variable or probability based in this, that you'll find that anybody who's getting into becoming a quantitative analyst or a quant or an actuarial analyst or a weatherman or anybody who's really involved in the dynamical systems would find these to be the regular tools in the field. Now, when I look over the titles of the sections in this book or the pieces from the symposium, it's very striking how they address at one time what's the simple thing as the behavior of a number over time, and what in the other sense is the extra classical part that is about this potential theory and how it all adds up in the middle, that it's potential what's conserved, and that is what makes for these continuity laws, how they really can all add up, and that this way we can find what are some real mathematics of infinity, because that is really what explains how things are. So then from the contents of this book, and it's edited by Joshua Chover and is published out of the University of Wisconsin-Madison in 1967. It's on the front of this piece is signed by Harry Hochstedt. Now, I've never met Harry Hochstedt, but I have here his book. It once was in his library from the Mathematics Research Center of the United States Army, and now is in my library. So this was printed by John Wiley and Sons. And so considering the titles of the works, Construction of Markov Processes and Axiomatic Potential, Hunt Processes and Standard Processes, Markov Processes with Infinities by Kai-Lei Chung from Stanford, and Kai-Lei Chung is the name that sticks out. Semi-classical potential theory, excessive functions for a class of continuous time Markov chains. Now, when we think of a continuous time and discrete time, is the idea, for example, of the notion of continuously compounding interest vis-a-vis interest that compounds on regular notions. And then for things like the rule of 72, that according to the rate, you can determine by multiplying by 72 what would be the time for that to double as a numerical coincidence that's pretty much close to things when trying to figure out the ways to approach, again, that extra classical setup, the ansatz, the Gedanke, with readily available tools. That's just an example of, in terms of the continuous time and then the discrete time, these kinds of things. And then they go on to read excessive functions for a class of continuous time Markov chains, on random time substitutions in the Feller property, on the multiplicative decomposition of positive super martingales. The martingale is the gambler's dilemma. It's basically, if you have enough money, that you can always just double or nothing until you walk away with the winner. But eventually, the idea is that the house has always collected more money or has some limit on the table, and so the martingale goes bust. But the idea is that eventually a random walk will result not just one direction. It's not necessarily so. One way to think of that is this. If you consider all of the sequences that are 0 and 1 sequences, every single possible 0 and 1 sequence. So an infinite sequence of either 0 or 1, and every single one of those that there could be, from 0, 0, 0, dot, 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 to 1, 1, 1, dot, dot, dot. And that, for example, in the middle you expect to find 0.01, dot, 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 and right next to it 0.10, dot, dot, dot. And so that when you take a look at that and figure out that it kind of works up that half of the sequences have equal 0 and 1 density. Half of the sequences have equal 0 and 1 density. And what does that mean? That means ergodically or randomly, stochastically, treating those as Bernoulli trials. Flipping a fair coin is also called a Bernoulli trial. The idea is that if you pick one of those sequences at random, it's 50% likely, approximately or exactly, that going over all that forever, that it would always be that there are star distributed in binary those. Then the other half of the sequences basically range from having all zeros to all ones. And so that gets into basically an heuristic in terms of just the properties of the space in zeros and ones. It's also called Cantor space, but this is a square Cantor space. That it so results that when you think about Bernoulli trials, flipping fair coins, and sampling real numbers as from between 0 and 1, by reading off the binary digits of the number between 0 and 1, that it's likely that you will arrive at one of these numbers, because according to the law of large numbers, there's about half as many heads as all, and half as many tails as all, and about the same number of heads and tails. Yet at the same time, there's certain random events that arrive that are not so. There is an incredibly unlikely, or among the least likely, or 1 over 2 to the omega likely, all zeros or all ones, all h's or all t's. This is the kind of thing that gets into establishing what are the contents of the space, because trying to figure out that from just the law of what they call the law of large numbers, given the law of small numbers, that when you start with a few and go on towards infinity and the unbounded, that it works out differently than if you start with the whole space and then determine from the columns are each half zeros and ones. That because every single column in that table, the nth place is half zeros and half ones in whatever various inverse order. And if you take a half and half and half and half this square table again, then you can find that the first digit is 0 and the second digit is 1. Meaning that the first half's first digit is 0 and the second half's first digit is 1. these are the kinds of things that result from applying the properties of the space to expect what are the expectations of the likelihoods of these things. Now, for something like a regular set theory, Cantor space is not square because this space of zeros and ones is the sequence of all representations of the subsets of the natural numbers, each nth place indicating the nth number, and 0 and 1 indicating its membership or lack thereof in a set. That's an uncountable set. And it so arrives in the Cantorian theory as a Cantor space that's standard Cantor space, not this square Cantor space, which is arrived at because there's a non-Cartesian function for them. Everywhere in Cantor space, all functions are Cartesian. That how it works up is that the probability of sampling an irrational number is much, much more than a rational number, because the rational numbers are countable and the irrational numbers are uncountable. So there's not really a means to say, except that those numbers are almost everywhere irrational, that if you flip a coin infinitely many times, it eventually will not repeat. A rational number is a number that in its infinite terminus will find a repetition, or that, for example, it just ends with all zeros, which are even fractions of powers of 2, inverse powers of 2. And so one way to think about that and how it's arrived at is that if you did flip a coin infinitely many times, and it did arrive at a rational number, how that works is that every time you flip a coin to get the next digit of the number, it's also the start of a new sample of a new number. So by the time you've sampled one infinite number, you've collected infinitely many samples, each one an infinite sequence of real numbers. It's kind of like by the time you fill up Hilbert's Hotel with this scheme, or in building out towards a space, or as a straight line out to infinity would do, then you've gathered infinitely many samples. So if you gather an irrational number, which is the digits don't repeat in an infinitely repeating terminus, then you've sampled infinitely many different irrational numbers. But if you sample one rational number, it results as a sample of that infinitely many times. The repeating part is sampled again infinitely many times. So this is an intuitive way to explain how, according to probability theory, and the difference between rational and real numbers, which are both sets dense in the reals, nowhere continuous, whose complement is each other, regardless of whether one is countable and the other uncountable, which in the real numbers any would be, pretty much, given what you construct they would be, because a construction involves the naming of the elements of things, and so it would be countable. Is that this way, it's a reasonable way to understand that, yes, the rationals are huge in the real numbers, and that their significance as samples, for example, as discrete values in that continuous number line, are heavier than these irrational numbers everywhere. So these are the kinds of things that go into a non-standard development, and what are so relevant to somebody who's beyond that they have a college degree in mathematics, beyond that they have a standard development and linear curriculum of an educational setting for science that sets them up for success because they know calculus and know how to do dynamical modeling, is that then these other things that add up are what are the intuit of the surrounds. And so for these other classes in this book from 1967, it includes, on the multiplicative decomposition of positive supermartingales. So that's basically the idea of sampling a supermartingale is just sampling one of these infinitely many times. And polar sets for processes with stationary independent increments. Random walks on a line, that, as you can see, kind of has various ways to consider how it works. Potentials associated with recurrent stable processes. Application of unsmoothing of Fourier analysis to random walks. Penetration times and passage times. Here we think the course of passage is the straight passage of a line. Limit theorem for a class of branching processes. Shinzo Watanabe out of Kyoto University, Japan, and University of Washington, Seattle, Washington in 1967, has the last paper in the symposium proceedings, that is about a limit theorem for classic branching processes. So what I was most curious to start with is Bauer's construction of Markov processes in axiomatic potential theory. And so what this is going to advise us that there's a space where these processes go to, and this is what I call this square Cantor space. Now, it might not be available to the authors of this book because it involves resetting some of what are the standard axiomatic set theories, regular ordinary foundations, and the classical modern set theory, Zermelo-Fraenkel set theory, and all what's built up of that after Galois and stuff like that, which is above set theory. Then there are axioms. Least upper bound property of the reals is an axiom. Measure 1.0 is an axiom. The open topology is just picking one of the many possible topologies of the reals. It's an axiom. And thusly, a variety of suitable and compatible derivations in the inductive work out. This is it's so that Bauer will have a hard time establishing some of these things because this is where he'll have to be the talking around what he needs to approach to get to what it is, because otherwise he'd find himself in contradiction with mathematics. And here, as I've developed, that there's line continuity, field continuity, and signal continuity could much more readily and easily support what these continuum mechanics entail. And it's a pretty great thing. It's you know, I'm a reasonably well-focused person in terms of that, and for a long time I've been studying that. I find it beautiful and compelling. So let's see what he describes, because this will basically open this symposium. The ideas of G.A. Hunt about the potential theory of certain Markov processes have influenced considerably the development of the so-called axiomatic theory of harmonic functions. So all this nonlinear talk we've been talking about the theory of potential theory and the nonlinear components that add up for these things and the potential fields of electricity and magnetism, which are different than the lettered fields that are classical that everybody knows called Maxwell's fields, E and B. The other lettered fields like A, C, D, F, G, H, there's a whole alphabet of lettered potential fields in electromagnetism, and all most people ever know is E and B. But 120 years ago, they had already lettered all these different fields from the empirical study of all kinds of apparatuses and contrivances and configurations of experiment and energy. That's how it so arises that mathematics has a simple linear course saying you will learn E cross B, and this way you can determine the electromotive force called the potential difference, and that's called voltage. That really in this axiomatic potential theory, then what's being built from that is designed in terms of harmonic functions, because a harmonic function is basically established for waves. What are these echoes and echoes and echoes of the waves? The higher order waves. That for a wave, it has all its reflections up above it that make for that a discrete event, like in particle physics or quantum mechanics, that the particle is dually a wave, and that these harmonic functions make very well understood definitions about harmonics in a closed box, as we read often from Maugin, and reading that nonlinear electromechanical effects and applications of Maugin was really an insight into a lot of the developments that go into that for the near field and the far field, and the revolutive and the periodic and the cycles of waves. That these harmonic function theory then is what they call the theory of potentials today, but that's just getting like this algebraic, the differential geometry and these submersions and immersions where they're able to just kind of get out in that, so that each of these harmonic functions as it goes out is just kind of another immersion or submersion, and it gets closer, it gets more of the higher order terms that contribute all the total value to what is the real sum and mensuration of these things. That that is what is founding all these potential theories in the very fundamental Markov processes, or just the behavior of a number over time according to some formula that's restitutive and oscillative and oscillatory and dissipative and attenuative. That this is what the author indicates is this so-called axiomatic theory of harmonic functions. that it's kind of like the axiomatic theory of geometry with points and spaces and points and lines and dot dot dot, that ultimately is a theory of points and spaces, vis-a-vis a theory that starts with points and spaces and just has all those other things arise in the middle. That's this idea of the theory of the sum potentials. That's theory of this sigma or omega potentials, infinity potentials, that all add up to be the total. And so that is, for the intuitionist, something to arrive at that exists, because by the time you already have a universe in your theory, there's no point throwing it away again. It just makes for limited intuitions, which aren't necessarily sensible, fungible, and tractable, meaning that then we can compute numerical methods for them. But at the same time, is a necessary backdrop for the intuition, what otherwise would leave people bereft of much of a context to have any idea of what concepts are missing. So the so-called axiomatic theory of harmonic functions. Conversely, it was quite natural to ask whether, one, the non-negative hyperharmonic functions of the axiomatic theory of harmonic functions, in the sense of either M. Brelot, who's been mentioned before, or the author, Heinz Bauer, coincide with the excessive functions of a semigroup of sub-Markov kernels, which you might think of as, when we talk about the quasi, the pseudo, or the degenerate, these sub-Markov kernels, that a kernel is basically the machine, the automaton, that given an input produces an output that's somehow deterministic, and whether and that is contained in a small area, and out of it grows all these things, and whether too this semigroup is the transition semigroup of a Hunt process. And so here he's describing a Hunt process named after someone named Hunt. It's a proper name. That then one wonders whether that reflects this intuition just mentioned of the total cases of the point, local, global, and total. For the case of Brelot's theory, Meyer succeeded in giving a positive answer to problem 1, assuming that E has a countable base and that the non-negative constant functions are hyperharmonic. So we can read from this that the hyperharmonic reflects the usual parts of speech and etymology of words in grammar, according to our dictionary and the language, that hyper means above and hypo means below, that exothermic means releases heat and endothermic means collects heat. That here these hyperharmonic functions are expected to be like in the theory of subpotentials, above what is otherwise the order of the potentials or the order of the harmonic function in effect. Meyer solves a problem first for a regular set in E, which by definition is an open, relatively compact subset V of E, such that the Dirichlet problem has a unique solution H sub f for each continuous real-valued boundary function f, and such that H sub f greater than or equal to 0 if f greater than or equal to 0. So reading this, we can take already quite a bit from our earlier discussions about what's going on in here. We were just reading about the analysis and the Banach space, about the compact, and about Stonesek and compactification and Friedholm, or what goes into that. So here he's talking about that his solution is basically built on this. It's of one unit or one period. That the harmonic function is, and its analysis is compact in the sense is that most usual real compact regular spaces are having bounds, and that that is countable makes for that. Well, if it's uncountable, then that induces all sorts of things. So he's building up kind of the sticks or whatever, that he can make a stack of these sticks, whereas in the sense that otherwise it would be kind of trying to make it as more something that's the spaghetti or so, or cooked spaghetti, in the sense that there's straight lines of the segments, and what you can build from the countable is just the rationals. And so then it mentions the Dirichlet problem. Now Dirichlet is famous for a couple things, and one is the pigeonhole principle. It's like if you have a collection of pigeonholes, it's like a house on the roof where pigeons live, and some say the passenger pigeon went extinct, but really they're just all feral and everywhere around the urban areas. That this idea of the Dirichlet principle is that if every one of them is full, then one has to leave for another one to go in. Or that if there's a hole between every one of them, you can always put in another one. And so this kind of regularity is applied directly to ideas like the Hilbert's Hotel, which is, it's like numbered set of rooms, infinitely many, and people can move from room to room, and that kind of thing. So then the Dirichlet function is something along the lines of that it's 1 for the rationals and 0 for the irrationals. Now in the modern standard set theory, that would be that it's almost everywhere irrational. But for example, from the discussion before about this square Cantor space and the space that it attains to, as these terms here, is if you can read that they're developing, that makes it that the Dirichlet problem is the thing that still he has regular is about the open topology, that neighbors have points, that he can make arguments of the density of these things, that in the difference between any two standard rationals, there's still infinitely many rationals either. There's infinitely many rationals or irrationals. This is why when people take a topology course and they get to one of these theorems that makes an axiom or stipulation instead of a derivation, saying, for example, and thus because we decided that for this open topology that it's not the rationals. That there's any time you find an argument like that where you can replace terms just because they're nowhere continuous but dense in the reals, whose complement is each other in the reals, two sets that as a superfine comb come together to form a signal reconstruction in the real numbers, that this is something that again is usually left to the side because A, nobody ever thought different, and B, if they did, then they'd have to build all this other supporting stuff from the very bottom of the foundations. So Meyer solves the problem first, has a unique solution h sub f, continues to be revalued boundary function f for each of those, because he's basically saying, kind of like this uniform and dominated convergence theorems mentioned yesterday in the reading from the Taylor's introduction to PDEs, that it's that kind of thing, such that h sub f is greater than is equal to 0 if f greater than or equal to 0. This part of Meyer's consideration also applies after some minor changes to the regular sets of a space E. Of the space E, a regular set in E, that E has a countable base in the author's theory. Meyer then solves the global problem, and so anything I mentioned here about square Cantor space or all these notions of the coin tossing, those are in this author's theory, or me. Meyer then solves the global problem by a limit procedure which relies on the fact that a Bernoulli space E is covered by an increasing sequence of regular sets. However, this argument breaks down in the author's theory because there are simple subdomains of R squared which cannot be covered by an increasing sequence of regular sets with respect to the one-dimensional heat equation. This is that, I read this as that when something is to reach over a lattice and every point in it, that every point in this lattice as the differences go to 0, so that there's a point everywhere, and that it's square in the small, or that it's circular in the small. Those are two competing kinds of things, because on the one hand it's like the triangle inequality and the metric of the measure is used to box all the functions down. But on the other hand, it needs to have this free analytical basis for this is why he's explaining that it doesn't add up, for otherwise this one-dimensional heat equation cannot be covered. The argument breaks down. One could think of passing from the local case to the global one. Here recall earlier this ordering, point, local, global, total, that we talk about the local case and the global one, about the local case is about the point and the global one is about the space. One could think of passing this impasse. The impasse is that on the inductive side, it's not arrived at from the point side ever being a space, and it's not arrived at from the space side ever being a point. It crosses in the middle. It's called middle of nowhere, or called one half. That one could think of passing from the local case to the global one by using the results of Courage and Prioret about recollement of processes. Recollection, a reorganization. Besides the technical difficulties of such a procedure and the arbitrary capricious nature thereof, one would then arrive at a Markov process without information about the analytical behavior of the corresponding transition semigroup. And so the transition semigroup indicates the collection of the properties of the propagation of things, or the motion through things, the course of passage through things, the drawing of the line. That then the semigroup is basically a group with or without the other side of the inverses. That is forward or is closed going forward. And it is saying basically that would be disconnected from otherwise this development. And he's kind of explaining some of the things that go into why it's so interesting, difficult, challenging, and possibly rewarding to understand this theory of points in a space, as that's being geometry, and how to build that up from points to points and lines in Euclid's geometry, classical constructions of fundamentals, out to these spaces and the cutting of the spaces, or the terms, the segmentation of the spaces, that it arrives that they come together from this inwardly square, rectangular, orthogonal, and is according to our analytical basis from Descartes, and outside from the spherical and the spiral. Because it's built from inside from the spiral, the outside it can be a frame. This is the dialectical of the dualist monism for this dually self-infraconsistency, of this theory overall of mathematical objects, a universe of them. Besides the technical differences, recently Bobac, Constantinescu, and Cornea solved problems 1 and 2 by methods which rely heavily on potential theoretic considerations. This idea of the potential theory is that it adds up then to make a space in the local and global, that anything that would otherwise just kind of not admit anything but the inductive makes for that, then there's some kind of recitative or oscillating that gets so applied. These are these harmonic functions in effect, which show up in a vibrating string or any other thing that we can build from the applied, or springs and pots from the viscoelastic and this kind of thing, in pieces. That these are the considerations. Inspired by his work, Hansen, in his yet unpublished thesis, this was in 1967, pointed out that both problems 1 and 2 can be solved by first proving simple and useful extensions of a theorem of Hunt about the construction of a semigroup, that the sequence P sub t for t greater than or equal to 0 of sub-Markov kernels with given potential kernel V for the potential kernel equals the integral from 0 to infinity of pt dt. That just saying that we'll go ahead and sum them all up, and that's just a model of it. So he's like, yeah, this is a formula for it. It's insoluble, but it's a formula. And of a theorem of R. and Blumenthal about the construction of Hunt processes with a given Feller semigroup as semigroup of transition probabilities. So here what the author describes is that Hansen has described that given these mathematical objects with these forms that don't have solutions so necessarily, but do because that's what it is, that he offers that this would be the unanswer to both problems. And it's not yet to say that this would be the stronger condition, that this is a unique example for both problems, but it is at least an example. And so it's clear that the authors can point that out and approach how to solve such problems. And of a theorem of R. and Blumenthal about the construction of Hunt processes with a given Feller semigroup as semigroup of transition probabilities. So this is describing that there's some course that makes it so that it will be so fulfilled that it somehow arrives through the middle of nowhere, a straight line from 0 to infinity, both ends. A simple application of both results to the author's axiomatic theory of harmonic functions gives them positive answers to problems 1 and 2. This contribution to this symposium is a report on Hansen's results. For all notions concerning kernels, semigroups, and resolvents used in this paper, the reader is referred to Meyer's book. Meyer's book is called P.A. Meyer, probability and potentials. And probability, see, this is sort of a graduate course in probability here, and I'll be curious just what it might say about potentials, because usually it's just framed about the counting arguments, but we want to get into Bayes and then Jeffreys, but he does talk about limit theorems, and so that's usually the central limit theorem, and then but he describes some various strong limit theorems, and then as we get laws of large numbers, weaken strong laws of large numbers, weaken strong laws of convergence, and these kinds of things. And then the stochastic processes in Brownian motion in this book, and that continuity and non-rectifiability of almost all sample functions is one of the last sections in this book, graduate course in probability, which would follow, of course, a couple years of courses in undergraduate probability. So, carrying on, this Markov processes and potential theory then basically is this extra classical or superclassical side of what's being built up as at least the one-dimensional case. This is all, Markov process is the one-dimensional case in time of the value of a number, these kinds of things. Meyer's book. Our terminology in the theory of Markov processes is that of Meyer's lecture notes in the forthcoming book of Blumenthal and Cantor. All facts about the potential theory of a harmonic space can be found in H. Bauer's Harmonische Räume, that's harmonic spaces, and era potential theory, and their potential theory from Springer Verlag in 1966. So he then breaks down this into section 1 is construction of sub-Markov semigroups, and section 2 is construction of Markov processes with given transition probabilities, and that's about it's equipped with this semigroup that is built up in these algebras basically to find the desiderata and requirements of these things. And that 3 is the application to the axiomatic theory of harmonic functions. From now on, E will have an additional structure. We shall assume that E is a strong harmonic space in the sense of Meyer's book just mentioned. In addition, the constant function L will be assumed to be a hyperharmonic on E. Now, we might usually think of that as associated with length. The set of all hyperharmonic functions greater than or equal to 0, respectively of all potentials on E, will be noted by symbol DAG or star, respectively by big Rho. These assumptions are fulfilled in particular in the case studied by Meyer for Brelot's theory. So in this case, what I imagine to do, it'd probably be the best idea to study Brelot, B-R-E-L-O-T, and find out what all he's put forward, because it appears that Bauer and Meyer and Blumenthal follow him as follow Markov, who is linear and classical, with respect to Courrèges and Priore and Bobach, Constantinescu, and Cornea, about the Hunt process, so for Brelot and Hunt. So that's the kind of thing you get into when you're studying pure set theory and non-standard analysis, because it is the infinite part, and it's based on the fact that the space exists instead of that. It kind of seems selfish sometimes. It's like I start the numbers at 0. It's like, well, they already went to infinity. This is one of these things you can gain from having that abstractly, objectively, subjectively then, that Platonism, these ideals make for this thing exist. And then that with regards to the requirements and desiderata of mathematics is meaningless and useless if it's just an intuition. If it's not rigorous, formal, linear, and sensible, tractable, and after being fungible, and everything is closed in its forms, and there's no ambiguities or extra definitions, nor is there any possibilities of otherwise extending the domain. That's kind of what I say it is, but it's, total, as opposed to that being a local thing where eventually metaphor fails. And we talk about the strong metonymy as a good thing. So we read about a page from this book about Markov processes and potential theory with some context, with some intuition, and then this graduate course in probability. Is to be read because what interests me about that is we got a development of the central limit theorem in our probability courses, because that gets up to that then you can use for any mean with in terms of any distribution with a mean, a central local or global maximum of expectation, likelihood, probability, or chance. Those multiply together more and more after they're normalized and standardized by setting the width of that to only 0 and 1 and setting the height of that to only 0 and 1, makes for then that what is able to be built up after the central limit theorem is a number of ready and very well-known tests, so that you can establish these are the most fundamental tools in the statistical toolkit of what's called chi-squared and Student's test and Fisher's test and the t-test. And what these do, and I forget their particulars, but I could refresh on them. The idea is that then you can establish for a given sample variance of a given set of samples, with sampling with replacement and sampling without replacement of discrete distributions and continuous distributions, that you can treat most discrete distributions as sorts of continuous distributions, but they have much simpler counting arguments that build them. Besides that, all the calculus of the continuous distributions mostly involves integrals as about the exponentials and a bunch of different distributions. That any function that has area 1 is a probability distribution, but some various ones like beta and Weibull and Poisson and Gauss's normal distribution appear much more often. That anyways, besides these shape and scale parameters of these, after they're normalized and standardized into a box, and then that they're multiplied together, so the central limit theorem by the law of large numbers says that any distribution with a mean ends up looking like the normal distribution, then that these tests apply, and then that gets into our analysis of variance and analysis of covariance. That this is so far all been univariate, but then when we get to analysis of variance, analysis of covariance, and then there's a multivariate analysis of variance and multivariate analysis of covariance, that these are higher level courses in usual statistical degree, or that's what I got. I got about 15 or 30 credits of statistics in school, and that the idea is then that these laws of large numbers add up for a central limit theorem. But what that book also mentions before that is just the general concept of these limit theorems. And so it makes space for something that is this complement called the uniformization limit theorems. Because in the same way, sometimes these processes will go to like a straight line, then otherwise they'll just go to this uniformization limit theorem. And so that way you can get enough samples and say, I know I've gotten enough samples, because besides that it looks like it has a mean, it also fills out the sides. This is the kind of thing that can make stronger statistical hypotheses and stronger statistical tests, just to make it so that otherwise what ends up being the usual grab bag toolkit of people's statistical tests isn't invalidated because it's not enough. And so how that goes is that with respect to these limit theorems, and laws of large numbers, laws of continuity, and laws of small numbers, laws of numbers, and in time, in these continuum mechanics, that ends up being a pretty great thing. So most of what we talk today is about the square Cantor space, and the idea that it's non-standard and it's unattainable from our standard axiomatic descriptions of set theory, which is so important because that's also our linear curriculum, and also that it holds up our central results in real analysis, and that thusly then we read, and it was kind of described, and again, any mistakes are my own, whereas what these authors are talking about is pretty much exactly what I say, in the same direction, and much for the same purposes. that in this way, what is arrived at is why these retroclassical fundamentals, this is an Aristotle's continuum redone in modern 21st century set theory for these kinds of developments, makes for then that it's a top to bottom development and brings in all these things which are otherwise just unique and closed in the theories of the day as examples with complements that are their duals. Better, bigger, and better, and but yet it remains to be seen that it's not yet so developed. And so in that sense, it's yeah, in the sort of the barbaric state, I guess you could say. Although not to apply it to that, but it's in the more of the naive state. It's in more of the primordial state compared to a concrete jungle. It's like there's a fence that nobody ever crosses, and on the other side is a green field. There's not much action over there because everybody who lives in that city mostly doesn't believe the fence or the other side exists. But it does. And so that's a pretty cool thing. So if that's about the the sampling space and what goes down when it all goes out and there's a universe of zeros and ones, then something like this macroscopic theory is basically what wave theory is to particle theory. There is more state in the local for a particle than there is just in the particle. That would go on forever, given that in the linear laws of motion, that once it's set and there's no interaction with anything else, out it goes, principle of least action. There's that this wave encompasses more about it, and its wave does too, and this wave does too. And this is already built into theories like relativity. We have in this unified field theory that was mentioned up earlier, there's both relativity, Einstein's theories of general relativity and special relativity in that order, not in the order of special relativity and general relativity, the reverse wrong order, unless you want to just compute things for computer chips. It keeps things simple. It's like kind of like simple, like E cross B, the classical Maxwell fields is simple. And special relativity first, and then deriving GR on that is simple because it keeps a bunch of those equations much shorter and with less indirection. Whereas putting GR first then just has light as the breaking radiation when it comes in around it. Simple. And it can be written in a formula, so that way then the idea is to cross this impasse, cross the bridge, which these workers in the Advanced Symposium conducted by the Mathematics Research Center, United States Army since 1967 have been putting together, is just kind of needing for the physics needs that for continuum mechanics, and the financial and actuarial and statistical and probabilistic and such matters of dynamical modeling have that as real. And then that the idea is to figure out how these formulas work up to make those nice and neat, and then figure out the mojos that make what are either strong or weak laws of large numbers, when and where they apply, so that for things like this Dirichlet problem, which is like the signal continuity, or the Jordan measure, which is like this line continuity, and then the field continuity and its axiomatized 1.0 standard measure, that this tripos holds up, makes a table. So, I've been studying this for a long time. And now looking at this book about this macroscopic theories of matter and fields, this is kind of similar in the vein. So this macroscopic theories of matter and fields is like molecular chemistry vis-a-vis atomic chemistry. It is saying that there's the macroscopic behavior of the electrons. In our Democritan chemistry, chemical reactions are defined by elements of matter and their bonds, or lack thereof, and their electrical interactions and lack thereof, which are called bonds. And so we have, when we study since Millikan oil drop experiment and Young, J.J. Young, or J.J. Thomas, excuse me, since J.J. Thomas and Millikan, they basically figured out, it's like we've set the value of the mass of the electron and its charge too. The electron has mass and charge. You could give that a Heisenberg uncertainty with regards to the mass and the position and momentum of a particle. You could also apply that to the electron too. And the running constants make for that, the closer we look at these things, and every time they put up a bigger collider, the smaller those measured values get. That's not a surprise. It's supposed to be that way. It's for the configuration by the energy experiment of these running constants. It's great. So anyways, this thermodynamic approach to the basic variational equation for building models of continuous media, that's about helping to get the first law of thermodynamics and the second law of thermodynamics back together. Because the first law of thermodynamics is kind of relative. It's like, well, this calorie is like what's going to take to melt this ice cube, but it's still going to be all melted. Versus like, well, this second thermal law definition of calorie means what it goes to absolute zero and everything stops moving. So when we build that up, then we have to figure out the adiabatic and non-adiabatic and this kind of thing. And these are the kinds of ways that mathematics already knows and physics already knows a lot about why these things do and don't add up. But then trying to put that into a grab bag of intuitionistic handles on either side of it. So when it's hot potato on the one side, hopefully you can toss it to the other hand or not burn yourself with the hot potato, which is an important thing for frozen people walking to school because it's their lunch, and the only reason they walk to school with a hot potato is because hopefully by lunch it won't be frozen. Is that this kind of thing goes on in science, and it advises a lot of things. And then for the statistics, and when if you hear something like, oh, did you hear that 50% of the universe is dark matter? Why is that? Well, we added up relativity and we did a statistical test, and as far as we can tell, it's what's on the other side. It's like, what happened? Well, we got a bigger telescope, and well, guess what? It was like, now 85% of the universe is dark matter. It's like, ooh, what does that mean? It's like, well, matter is the only thing in our Newtonian pull gravity that holds anything together, and the farther we look, the more it has to be that all this stuff doesn't exist, that we don't know where it is or how it is. But if it doesn't apply, then everything is wrong. But we're figuring out. So empirically, we're doing great. In fact, we're finding this more and more present all the time. So on the one hand, it's like finding all this extra stuff. On the other hand, it's getting farther and farther away from science. So it goes on. It's like, well, how did it get from 50 to 85 to 90? How did you pick these numbers? It's like, well, I don't know, but I can most surely assure you it's going to go to 50 to 85 and then 90, and then it's going to go to 95 and then 98 or 99 and 99. It's like, how do you know these numbers? It's like, well, if you take the central limit theorem, and the variance is like, the standard deviation squared. And so there's a table that shows you the quantiles and a percentage of things that your expectation that the value is going to fall within a certain number. And so the first one is it's beneath the mean, it's 50%. And for the first standard deviation, it's 85%. And this next standard deviation is 90, then like 95, 98, 99, . And so if you look at the table of the way the normal curve kind of slopes down, it slopes back out a little bit, and it's in flex, and it's concave and convex, that when you hear about these numbers like 50, 85, 90, 95, 98, 99, and the science's bigger telescopes are establishing this great empirical fact, they're just more lost in space. So anyways, that amuses some people, it confuses some people, it enrages some people. Not me though, because I got a setup that solves it great. Preface. Academician L.I. Sedov, Institute of Mechanics, M.V. Lomonosov, Moscow State University, for a scientific description of mechanical and in general physical objects, media, fields, and phenomena, one must employ theoretical models. Mathematical modeling of physical space-time lies at the foundation of any theoretical interpretation of the world around us. At present, the main distinctive feature of the common idea of physical space-time is that of a four-dimensional continuum of points, each of which is given by a set of four numbers, the coordinates with one of those numbers being of a temporal nature, which is reflected in the geometric properties of the four-dimensional continuum. There are different ways of giving a concrete physico-geometric interpretation of the mathematical model of space-time. In Newtonian mechanics, as we know, a three-dimensional Euclidean space is used as the model of space, while time is considered a scalar. Special relativity postulates that a pseudo-Euclidean space is the model for the four-dimensional physical space-time. Finally, in general relativity and its many generalizations, we assume that the four-dimensional space-time is Riemannian, while locally it is pseudo-Euclidean, the case in special relativity. There are also other interpretations of models in space-time. The problems of, there's another paragraph. At present, many scientific centers, further developing the ideas of general relativity and its application to specific physical and astrophysical problems. So that is to say that there is certainly a large body of work under lock and key and buried under about 5,000 tons of cement and that has very strong intuitions all about real continuum mechanics. The problems of individualization of points in a gravitational field, energy, internal interactions in a gravitational field, and a global proper time connected with a choice of reference frames have been largely solved. There is a solution. There's not necessarily shown that it's a unique solution, so they may well be incomplete. However, the final incorporation of theoretically and physically correct notions and model interpretations must be linked to special observations of natural phenomena and to laboratory experiments, or built out. In other words, the basic idea of the covariance of physical laws still requires considerable explanation, vis-a-vis a totally fundamental theory. This is especially true when we deal with such basic characteristics as mass and energy, or the potential thereof, like mass and charge if fall gravity makes the potential, with asymptotic freedom, as was discovered in the 1970s in the middle of the nucleus, strong nuclear force. Since the main physical laws are formulated only for individualized volumes of various fields and parts of matter, and this requires the introduction of special reference frames so as to individualize the various objects. That's this point in wave modeling. That's a great little introduction to this book, and helps explain the tremendous amount of knowledge that goes into what he knows about these things. Well, I hope this was interesting, enlightening, and insightful. I hope it's a good tone. You know, I hope that if your sleep deficit is one way, that it's a nice steady drone. If it's the other way, it brings those the arrows of light or whatever, kind of like some people have a good sip of coffee might do, the light bulbs. And at any rate, regardless, that's this author's opinion. So long.